Good day, folks. This is video number 23 in the motion design playlist for solving dynamics problems. Motion design is an application which is buried in the 3DEXPERIENCE platform, and actually it has its roots in a different software called Simpac, but that's okay. Videos 23 and 24 are solving the same problem. Let's concentrate on 23 right now. It will be using a roll curve joint to model the problem that you see here. So we have a smaller cylinder that is inside of a bigger cylinder, it's outer one, and somehow it is rolling on the surface. Okay. So it's a pure rolling problem, and I'm going to be solving this with a roll curve joint. We assume that the surface is frictionless, uh, and just keep in mind that rolling does not take place without having some friction. However, in this problem, I'm going to assume that rolling takes place somehow. I'm not going to even model the friction, because when you use roll curve joint, that frictionless assumption is by default what's going to happen. Okay. Uh, Now, uh, there are some numbers that I'm going to specify: the radius of the big cylinder and the radius of the disk. But this is the kind of problem that you solve in an introductory vibrations course. And for the solution to this problem, you can look at this last this reference at the very bottom, and it's going to give you, it's a single degree of freedom system, because we are assuming it's rolling, and theta is the degree of freedom, and this is the differential equation of motion. Now, if theta is a small, in other words, if we release that cylinder from relatively small angle with respect to the top origin, so about 10 degrees or so, this can be linearized, and you get the differential equation that you see here, the kind of thing that you see in a linear vibration analysis. So this plays the role of mass. Obviously, mass is not here. This plays the role of mass. This G plays the role of stiffness. So we can find the natural frequency of the vibration, oscillation, and period is going to be this. Now, with these values, this period comes out to be 2.33. However, I will not release it from small angle, or release it all the way from the top. So it is going to be an oscillatory motion. Actually, here's the differential equation, but the period is different. It's not going to be this. You'll see that. Now, yep, let's go ahead and do this. Let me start with an assembly. There we are. I'm going to insert my first piece in it, which is going to be, let's say, the track. So insert, or the outer cylinder. So insert 3D part. This is going to be my outer cylinder. Let me first call it that. Outer cylinder. Copy paste here. I'm going to make it yellow. Okay, let's go make it. So on that vertical plane, we'll sketch. Make my job easier, I'll sketch an arc with the center over there. And let's give it a radius. This is going to be 1 meter inside radius. There we are. And I'm going to complete the rest of the geometry. So another arc for the outside border, something like that. And then I'm going to draw my lines to close it up. Where's the other one? Okay, and exit. I'm going to pad this thing by point, uh, 0.2. There we are. And then I'm going to insert my small cylinder. So insert. You know what? I'm going to make this thing a little bit longer. Instead of 0.1, 0.2, I'm going to make it 0.4. Doesn't really matter. Okay, so insert the, go all the way in the top, insert another 3D part. Okay, I'm going to call this thing rolling cylinder. So properties, rolling cylinder. Copy this, paste it there. Let's make it orange. Okay, so on purpose, I'm going to draw it on this face. I'll sketch. Let me actually get to the 3D part here. On that face, I will sketch. Okay, a cylinder or a circle right here at the very top. Circle. Let's give it a radius of 0.1. And let me make the distance from this point to that as 0.9, so it makes this tangent. So let me create a distance here to here, 0.9. That makes it tangent. Good. So exit, and I will pad it. See which direction am I looking at? Yeah, by point, I don't know, 0.2 maybe. Let's see how it looks like. Yeah, that's good. That's good. Okay, we go all the way to the top. Oh, by the way, while I'm in this cylinder, while I was making this roller cylinder, let me create a point, and that point is going to be exactly at the center of the circle. So, circle, center, right there. So a point has been created here, because later on I'm going to look at the motion of this point. Okay, good. Now we go all the way to the top. Let's apply our engineering connections. So engineering connection, let me fix the outer cylinder. That's fixed. You can see that. Outer cylinder is fixed. And then I'm going to create a roll curve joint. We go here, engineering connections, and find the roll curve. Roll curve. It's asking for two curves that are, obviously they have to be tangent to each other. So, or touching each other. So this and that. Okay. And then you say, okay. And I will also create a planar joint here. You'll see why. You'll see why. Because if that joint is not there, these two curves can still roll on each other, but this thing can tilt. So I will do another connection, engineering connection. So this one is going to be a planar. I'll use this template, two planes. So that plane and this plane, and make a new connection. There we are. Click, close these. Excellent. Now we are done here. So there's my roll curve. There's the planar one. Let me update these things. Now we're going to go to motion design. It immediately creates a mechanism with those two joints in it. This is the name of mechanism, of course, mechanism one. Okay. Good. Notice what happened. There is gravity that's acting down right there, 9.81. And there are two bodies created here, the outer body, and these have their own markers. Well, what I'm going to do is I'm going to create a marker right at this location. So how do I do this? So I go to marker right there. See this marker? And I want to create it on this rolling cylinder. And by geometry, make it by geometry. So select that point that I created, either from here or from the tree, whichever is you prefer. So here, for example, and then we say okay. Now, before we go any further, now that I create a marker, I'm going to create a probe, basically, kinematic mechanism, a measurement, kinematic measurement, and I'm going to select that probe that I created, that marker that I created. You can select it either from here or from there. That marker was not absolutely necessary, but it makes my job easier. It was marker number 3 right there. You can say, even if I try to select this, it's going to select I believe the marker. Let me see for a second. Yeah, let me select this point. See, the marker is selected, and then we say okay. Good. Now we're pretty much done here. So first of all, the mechanism has been created. The duration is a dynamic one for 5 seconds. I'll just leave it the way it is. And notice that, this is good. So we say, okay, and let's run it. So I go to simulation and run analysis case. Just give it time. Assuming that there were no messages, no errors, it says succeeded. Now we're going to go and select our result. This is dynamic step result. Select this. Go to results tab. Play animation, and let's see. It goes like this. Yeah. Reset. Let's play it continuously. We can slow it down so we can see it better. Yep. Good. Now, I want to remind you, friction is not playing a role here. I didn't do anything with friction. That's what happens when you do these roll curve, or basically these kinematic joints. So we say, okay, no problem. Now, if we go and plot 2D plot, you go to 2D plot, you can go to kinematics measurement and say, show me, for example, the position of X. Position of X is fixed, whatever that X is, but the Y and Z are changing. For example, if you say, show me the Z at plot, this is what you're going to get. Now notice that the period actually, let me do instead of this, let me do the Y. So let me do the Y, the plot. Okay. So when you look at the period is roughly, see, starts here, it goes like that, which is roughly 2.7. It is not that 2.33 that you were getting, okay, based on small oscillation formula. Okay, it's not like that. And also, this is not it's a sine anymore. you know, Now, if I had used, let me say, okay, if I had used, close that. If I had used, instead of 90-degree tilt, if I had drawn it so that it actually fell from anywhere which is less than 10 degrees, this is going to be considered a small oscillation. And then what you're going to get is results which are not contact. Not this. This is not the right one. Right there. Less than 10 degrees, basically these formulas will apply and your number is going to be very close to 2.3. Okay. Now, the last thing I want to show you in this tutorial is what happens if I go and actually delete that joint, which was planar. So let me see now. Here's my planar joint. Right click. Can I deactivate it? I can't deactivate it, so I'm going to delete it. Okay. Now we're going to run it again. Simulation. Run it again. Now it fails because this thing will actually begins to tilt. Okay, and that's the reason that. Well, let me do it a different way. Let me go ahead and let me go to my joints. Where's the joints? These are the joints. Okay, let me delete this. Okay, let's try it now. See if it still says fail. Yeah, this one says succeed. The reason it said fail because I had to delete it somewhere else also. But anyway, it ran without the planar joint. So let's go ahead and select our result, dynamic step result, and go to the results tab, play animation, and let me show you what happens. Whoa, okay. It is, look, those curves are rolling on each other. You can see that. Those curves are in fact rolling, but those curves are rolling. But that planar prevents it from sticking out of that bar. Now, we're going to go to tutorial video for 24, where actually I will not use the roll curve joint. You see what happens. That's pretty much it. Good luck.